Today, I think we will focus just on Fourier's theorem and uniqueness. Now, I know that people might have been busy on Friday or not have had chance to view the Friday lecture videos, so I will recall some of the statements. I won't prove them. The proofs are all in the Friday videos, but I will try to show what these things were, at least, in case you haven't looked at them very much. So this lecture is all about conditions that guarantee us to express a function as a sum of its Fourier series. And there are many theorems of this nature. I will stick to the easiest ones, just the easiest one to state. So, okay. So our plan is that we have these tools, and I'll soon say what these are. Orthogonality, that allows us to find coefficients. There is a condition on the coefficients an that guarantees convergence. And then, well, one has to ask, if you know what the coefficients are, if you know how good they need to be to get convergence, when do you get that estimate? So this is where the C2 condition comes in. So these three already tell you that you do get some sort, that this series, when you appropriately define it, converges. But the last thing, the last piece of this puzzle that is missing is that this has to actually equal the original function, not something else. So you could think of this issue that comes up in problem part 4. It's a little bit analogous to when we said that if you have the differentiated sequence, this differentiated series, the assumption is that this converges to some function g. And then later we realize that this function, as a consequence of that theorem, is actually equal to the derivative of the series. So we know, first we usually have to prove that it converges, and then we discuss whether it actually equals what we started with. So 1 through 3 were discussed in the content on Friday, and we'll state this theorem soon more rigorously, but this is what I call Fourier's theorem. So the main things here are that you have to be 2π periodic, twice continuously differentiable. Then you can express f as a sum of its Fourier series, where the coefficients have a formula. We'll see this formula soon again and where it comes from. And that this convergence of this doubly infinite series is uniform. And one thing you might want to know is this is a double infinite series. It's a little different than most of the series we've talked about. But when I mean that converges uniformly, is that when you send both the top and the bottom index at the same speed off to infinity. And some notation just in case you haven't seen it. So we have this basis of functions e and x, which is e and theta, which is e to the I n theta. And this was this sine, cosine n theta plus I sine n theta. So this was a convenient way of using this complex imaginary unit to both include the cosine modes and the sine modes. That way we don't have to use so many trigonometric identities. And if we have two complex valued functions, then we define the inner product on the space by an integral f times g. There has to be a conjugation because we have complex valued things. And then we normalize the thing by a factor of 2π. So now, what did we do on Friday with these 1 through 3 more rigorously? So the first tool of these Fourier series, and these are listed, by the way, on the YouTube by tool 1, tool 3, tool 1, tool 2, tool 3. So you'll find these essentially by these titles and numbers. So one is that these ENs, with respect to this new inner product, even though these lie in an infinite dimensional space, they behave like orthonormal vectors, meaning that the inner product between pairs of them, distinct pairs, is 0, and if you take a pair with itself, you get 1. So the picture to have in your head is that this is some sort of an orthogonal basis, but one that just keeps on going. So it's higher infinite dimensional. There's another vector, etc. It's hard to, of course, draw that faithfully, but imagine an infinite collection of orthogonal vectors. Now, there's a standard way of expressing if you have a basis. How do you express the function in that basis? Well, if you can figure out the coefficients by actually going in the reverse. Suppose that it was equal to such a thing. And since we have an infinite sense, let's for the moment disregard the convergence issue. If you'd fill in this argument, you'd have to add some convergence argument, but let's say in some sense. I'll say something about that in a bit. But then we can compute the coefficients using orthogonality as we take the inner product with EM. Well, what is this inner product? This is the inner product of this thing with EM, and everything here is linear, and everything ought to converge, and this is where the sum sense comes in. So if we take an inner product of this infinite sum with that element A, what we get if we pull everything inside is AN, EN, EM. But then we get this familiar thing that only one term survives. Only the term where n is equal to m survives, because otherwise we get a 0 factor here. So the term that survives is AM, and this is what we define this as, we'll a few times use this notation as the mth Fourier coefficient of f. The indices here go, by the way, from are integers, not natural numbers, as often you might see. Okay, so there's a formula for discovering these coefficients, and we will make this in some sense precise. For us, it will mean uniform, but I will remark that it actually doesn't depend on what it means. So if there is any way that you can write a Fourier series, even in the weakest sense of convergence that you might encounter, then this has to be the formula for the coefficients. So these are the Fourier coefficients, sort of with or without, regardless of how you think of this as converging. And that's a pretty powerful idea. But this calculation is one way of justifying it, even though it's a bit hand-wavy in this part. Okay, so you know what the coefficients ought to be, but then you have to ask, when does this thing converge? So the easiest thing is we want to apply Weierstrass M-test. And how can we do that? Well, we know that norm of En is absolute value of e to the in theta. Well, it's sine n cosine theta, sine n cosine n theta. So when you compute the norm of that, you always get 1. So the only part of that contributes to the norm is an. Another reason why this is useful. So if you want to bound the absolute values here by some mn, then really all you need is a bound for an, and all you needed for that to be summable. Well, what is the easiest summable thing to write? 1 over n squared. Well, 2 to the minus n is also good, but 1 over n squared is better because that is actually useful. Okay, so if we have such a condition, then we get uniform convergence. And that's part 2 of this game. But then you could ask, the third part is, when do you get that condition? And that's where the C2 condition comes in. If you get C2 and apply a trick of integration by parts, well, I'll mention that later again, then we get the coefficients decaying fast enough. Well, why do we care about this again? So what do we get from 2 plus 3 is that if we define the coefficients in that fashion, well, that was motivated by 1, f is twice continuously differentiable and 2 pi periodic, then the sequence of partial sums of this converges uniformly to some function g. So it's converging uniformly by part 3. So by part 3, it has the estimates for the bounds. Part 2 gives you the uniform convergence using Weierstrass M-test. So it converges to some function g. But what we need, what is the question? These are a little bit disorganized. Why is f equal to g? This slide is there only to really say that these are not nearly sharp conditions. So you could weaken the C2 assumption at the endpoints a little bit, or well, the continuity of the second derivative as well, by assuming that the second derivative exists and is bounded everywhere except at the endpoints. It doesn't have to exist at the endpoints of some, or finitely many points. It doesn't have to exist. So there's this point. It's just for writing out simpler examples, but we don't really need that. But okay, so C2 gives us easily this decay condition, and you can weaken it if you want. But why is this function that we get, this g, which is the sum of the Fourier series, why is that equal to f? There's no reason for it to be equal to f, just by what we have said so far. Well, the idea is that we use that heuristic calculation. Well, we know by definition that the nth Fourier coefficient of f is an. But if we compute the nth coefficients of g, well, it is the Fourier coefficient of this series. And let's again recall that, how that calculation works. So if you take the inner product with e to the I, let's use a summation by m here, and e to the I n theta, then it picks out the only term where m is equal to n, and it will give us an out of it. So these functions, g and f, whatever they are, they're two continuous functions with the same Fourier coefficients. Now this is quite remarkable. You have two random functions that have the same Fourier coefficients, and the idea is to prove that they are the same. So there's some uniqueness in this game. This is one of the main tools. What makes Fourier series works is this uniqueness component.